Good afternoon, class. Today we're going to talk about Chapter 2. Initially, we're going to talk about the metric system and the international system of units. So most of us likely grew up in America, where we use an American system. We measure length in inches, feet, miles. We tend to measure volume in things like gallons, cups, depending on what you're measuring. Masses, we tend to use ounces or pounds. And temperature, of course, we use the Fahrenheit system of measurement. However, many other places in the world, they use the metric system. Many years ago, scientists all got together and decided they were going to standardize everything, and everyone was going to use the same system. They named this system the International System of Units and abbreviated SI. The SI system is based on the metric system. For example, the measurement of length in the metric system is the meter. The meter is abbreviated with a lowercase m. In the SI system, it is the same. So it is the meter abbreviated lowercase m. For volume, in the metric system, they use the liter, abbreviated capital L. In the international system of units, they use the cubic meter, which is abbreviated with an m raised to the third power. For mass, in the metric system, they use the gram, which is abbreviated lowercase g. In the SI system, they use the kilogram, which is abbreviated kg. For temperature, in the metric system, they use the degree Celsius. In the SI system, they use a unit of measurement called the Kelvin, which is abbreviated with a capital K. Time, of course, everyone the world around uses the same system. So time, we use seconds, which you should all be familiar with, abbreviated lowercase s, and that is the same for the SI system. Okay. Volume, which is one of the measurements we just talked about, is the space occupied by a substance. The SI unit of volume is the meter cubed. However, in the metric system, volume is usually based on the liter because we tend to measure the volume of liquids a lot more often than we measure the volume of solids. The liter is slightly larger than a quart. You may be familiar with a liter here in America if you've ever gone to the store and bought perhaps a liter of pop. Right? We typically tend to buy our pop in 2-liter bottles, but they do sell 1-liter bottles. So if you're ever curious as to what a liter looks like, go to the store and pick up a 1-liter bottle of pop, and you can then take a look at that. So temperature. Temperature is an important set of units, and it tells us how hot or cold something is. As I said, in the metric system, we use the degree Celsius. In the SI system, we use the Kelvin. The magnitude or size of 1 degree is the same in both the Celsius and the Kelvin. In the Celsius system, water freezes at 0 degrees and boils at 100 degrees. 100 degrees Celsius, not 100 degrees Kelvin. Let's erase that real quick. Okay, 100 degrees Celsius. The Kelvin system, a degree is the same size as a degree Celsius. However, we didn't want any negative numbers. So 0 degrees Kelvin is the lowest possible temperature ever able to be achieved. It is the lowest possible. So you cannot have negative measurements, negative degrees in the Kelvin system. Otherwise, the two systems are very much the same. One reason that the SI system was based on the metric system is that you can increase or decrease the size of your unit by adding a prefix. There are some prefixes that decrease the size of a unit and some that increases. For example, milli and micro are used to make smaller units. Okay. There are many prefixes. Prefixes that increase the size of the unit from kilo to mega to giga, tera, and peta, and prefixes that decrease the size of the unit from deci, centi, milli, micro, nano, pico, and femto. There are some units that you need to be familiar with. The ones that you should be familiar with are the kilo. This is very important. The kilo, the centi, and the milli. These are the units you should be very familiar with. So, for example, 1,000 meters, oh, not 100, 1,000 meters equals 1 kilometer. Now you can use this for other units as well. 1,000 grams equals 1 kilogram. 1,000 liters equals 1 kiloliter. As I said, centi and milli decrease the size of the unit. So for example, 100 centimeters equals 1 meter. Okay? You can also do the same for liter and gram. 100 centiliters equals 1 liter. 100 centigrams equals 1 gram. Milli decreases by 1,000, right? So 1,000 millimeters equals 1 meter. And again, you can do the same thing with gram or liter. 1,000 milligrams equals 1 gram. 1,000 milliliters equals 1 liter. Any of these other prefixes, should you need them on an exam, they will be given to you. But kilo, centi, and milli are ones you should know. The cubic centimeter is the volume of a cube whose dimensions are 1 centimeter on each side. Right, so 1 centimeter cubed is equal to 1 milliliter, and they are often used interchangeably. Now, if you have a cube measuring 10 centimeters on each side, i.e. 10 centimeters times 10 centimeters is 100 centimeters, times another 10 centimeters is 1,000 centimeters, which is the same thing as saying 1,000 milliliters. 1,000 milliliters is equal to 1 liter. Therefore, in order to convert back and forth, 1,000 centimeters cubed is 1,000 milliliters is 1 liter. We are talking about measurements and numbers. Well, there are two kinds of numbers out there. There are measured numbers and exact numbers. Exact numbers are numbers that you do not have to measure. Okay? They are things that you can count. For example, if I ask you how many books are on your desk right now, you might tell me there are 2 or 3 or 4. Right? But you would always give me an exact number. There are exactly this many books on my desk. Another example of an exact number is a definition within the same measuring system. For example, 1 quart equals 4 cups. 1 kilogram equals 1,000 grams. 60 seconds equals 1 minute. Those are all exact numbers. There are exactly 60 seconds in 1 minute. Exactly 60 minutes in 1 hour. Exactly 1,000 grams in 1 kilogram. Right? These are not measurements that we've made. These are exact numbers. Exact numbers do not have significant figures, which we are going to talk about next. Measured numbers are numbers that you have actually measured, whether you yourself specifically measured them or an instrument measured them for you. In order to measure something, you would observe the numerical values of the lines, estimate the value between the marks. The estimated number is the final number in your measured number. So for example, if you were going to measure the length of a string, okay, looking at your ruler, you can say, okay, it is more than 1, 2, 3, but less than 4. More than 3, but less than 4. So the first number in our measurement is a 3. And then, looking at the dividing lines between, right? Looking at the dividing lines, if you follow along where this falls on our marker, we can see that it is more than 1, 2, 3, 4, more than 4, but less than 5. So we know that our measurement is at least 4. More than 4, but less than 5, so 3.4. Now comes the estimating portion. We know that it is more than 4, but less than 5. Looking at where that falls, I guesstimate that it falls a little bit closer to the 5 than it does to the 4. So I am going to guess that it is approximately 3.47. Somebody else might look at this and estimate 3.46. Or someone else might look at it and say, you know what, I think it's even further. I think it's 3.48. As you can see, that last digit is where the estimating happens, and since we all estimate differently, that is where the error or the uncertainty comes in our measurement. So whenever we have a measurement, we have what we call significant figures. And significant figures tell us where the uncertainty is in our measurement. So significant figures are used to represent the amount of error associated with a measurement. All non-zero digits are significant, meaning any number between 1 and 9 that is part of your measurement is always significant. Then when it comes to zeros, we have 3 types of zeros. The first type of zero is called a leading zero. So any zero that starts off a number, right? For example, 0.004. Any zero that starts off a number such as these is called a leading zero. Leading zeros are never counted when you're looking at significant figures. So leading zeros are never counted. Our second type of zero is called a sandwich zero. Sandwich zeros, or captive zeros as they're also known, is any zero that is between 2 numbers that is not zero. For example, 404. This zero is between 2 numbers that are not zero. Does not matter how many zeros there are, for example, 40004, as long as they are bracketed by 2 numbers that are not zero. We always count those. So captive zeros always get counted. Zeros at the end of a number are a little bit tricky. If there is a decimal point, for example, 1.00, if there is a decimal point anywhere in your number, the zeros at the end of the number do count. We call these trailing zeros. So here we have a decimal point, therefore these 2 zeros count, and this number has 3 significant figures. If you have a 0 and no decimal point at the end of your number, then the zeros do not count. Okay, so let's show this. Okay, let's see how this looks. For example, if you have a number, 300 meters, and you wish to show that the first and second zero, or the first 3 rather, and the second and the first 0 are significant, you would have to write this in scientific notation, because the number 300 as written, right, with no decimal point, contains 1 significant figure. If you wish to show 2 significant figures, you must put a decimal point in. However, the only place at the moment you can put the decimal point in is here. This would show that the number 300 has 3 significant figures. Since we want 2, we would write it in scientific notation. 3.0 times 10 to the 2. This shows us we have a decimal point and 1 0. So we now have 2 significant figures. Does everybody remember how to write numbers into scientific notation? Remember that when writing in scientific notation, we place our decimal point after the very first number that isn't 0. Then we write the multiplication symbol, x times 10, and we raise that 10 to the power of the number of decimal points that we moved. In this case, 2. If you are moving the decimal point in the other direction, if you are taking a number less than 1 and writing it in scientific notation, your exponent should be negative. For example, 0.0030. If we wish to write this in scientific notation, we would put our decimal point after the number that isn't 0, 3.0, right, times 10. Now we're going to raise this, right, to a power. We moved the decimal point 1, 2, 3 spaces. So our exponent is going to be a negative 3. Negative 3. Okay? So again, just to recap, zeros at the end of large standard numbers without a decimal point are not significant. Okay? When we write them in scientific notation, we don't show those zeros unless there was a decimal point in the number originally. Zeros at the beginning of a decimal number are used as placeholders and are not considered significant. We call these leading zeros. Zeros in between two numbers that are not zero are considered sandwich or captive zeros and are significant. So let's try some examples. 0.002650. We want to identify the different zeros. The first three zeros, the 0.00. What kind of zeros are those? Those are leading zeros. Leading zeros start off a number. Leading zeros are never significant. What other zeros do we have? Well, we have a zero at the end of the number. That zero at the end of the number is a trailing zero. Since there is a decimal point present in our number, right here, that zero is considered significant. Therefore, in this number, we have 1, 2, 3, 4 significant figures. The 2, the 6, the 5, and the final 0. So let's write this in correct scientific notation. We are going to take the decimal point and place it after the first number that isn't 0, i.e. the 2. 2, decimal point. Then we are going to add in the rest of the numbers. 6, 5, 0. Add an X and a 10. Now we are going to raise this to the number of places that we had to move that decimal point. So we moved that decimal point 1, 2, 3 places. We moved that decimal point 3 places. So our exponent is a 3. Now because this number is less than 1 to begin with, our exponent is negative. So this is times 10 to the negative 3. Let's try the next example, 43.026. There is only one zero in this number. It is between a 3 and a 2. Therefore, that zero is a captive zero, or sandwich zero. It counts. So the number of significant figures is 1, 2, 3, 4, 5, i.e. everything in that number, the 4, the 3, the 0, the 2, and the 6. 5 significant figures. Let's write this number in scientific notation. We are going to put the decimal point after the first number that isn't 0. That is the 4. 4, decimal point, 3026. X and a 10. Now, how many places did we move that decimal point? Well, we only moved it one place, right? One place. Since 43 is larger than 1, our exponent is going to be positive. So this is 4.3026 times 10 to the 1. Let's look at the next part of the example. It says identify the numbers below as measured or exact and give the number of significant figures in each measured number. 3 coins. If I ask you how many coins in your pocket, is that a counting number? Is that something you can tell me exactly? I believe so. Yes, 3 coins is an exact number. Therefore, it has no significant figures. Exact number. Okay, we do not count these numbers when we're looking at significant figures. The diameter of a circle is 7.902 centimeters. Is this an exact number or a measured number? Is this something you can count? The answer is no. Is this something you must measure? Yes. Is this something that is a comparison of 2 units within the same system? No, this is not a comparison. This is an amount, as in the diameter. It says the diameter is 7.902 centimeters. Therefore, this is a measured number. How many significant figures does it have? Well, 7.902, right? The 7, the 9, and the 2 are all significant because they aren't 0. The 0 here is what kind of a 0? I would say that is a sandwich or a captive 0. It is between the 9 and the 2. Therefore, it is always significant. So the answer is 1, 2, 3, 4 significant figures. 60 minutes equals 1 hour. Is that a counted number? Well, yes, in the sense that there are 60 minutes in 1 hour. There are always 60 minutes in 1 hour. You could count them, I suppose. But it is also an exact number because minutes and hours are within the same system of measurement. Therefore, this is a comparison of units within the same system. So this is an exact number. And we do not look at significant figures within exact numbers. So now, what happens when you need to round to get the correct number of significant figures, right? How do we round numbers? Well, we look at the number following the number that we wish to round to. If it is 4 or less, then it is dropped, right? Or becomes a 0, depending on the circumstances. If it is 5 or greater, then we increase the last digit to be kept by 1. For example, 138. If we wish to round 138 to two significant figures, right? The first two would be the 1 and the 3. The 8 would be the number that we are losing. Is 8 5 or greater? Yes, it is. That means that the 3 is then increased by 1. 1, 4. Now, can you simply just drop the 8 and lose it? Is 138 rounded to 14? The answer is no. If the number that you are dropping is before the decimal point, whether the decimal point is shown or not, you must give it a placeholder 0. Therefore, it is 140. 140. 138 rounds to 140. You can think of it as if you had $138 in your pocket and your friend asked you how much money do you have. You might round it up in your head and say, yeah, I have about 140. You would not say, yeah, I have about 14. Right? So if the number that you are rounding comes before the decimal point, whether the decimal point is shown or not, you must put placeholder zeros in. All right, let's try some practice. Let's round off 8.4234 to three significant figures. Okay, 8.4234. Oops, 4, 2, 3, 4. So three significant figures, right? We would cut it off between the 2 and the 3. Between the 2 and the 3. Is 3 larger than 5? No. So therefore, our number when rounded off is 8.42. Let's round that number to two significant figures. Hold on. Doesn't seem to want to recognize my pen. There we go. All right, let's try that again. 8.42. Oops, and I did it one more time, didn't I? Erase that. Okay. 8.4234. Okay. Now we want to round it to two significant figures, right? So we're going to cut off between the 4 and the 2. Is 2 smaller than 5? I believe it is. So our final answer is 8.4. Okay, let's try another one. Okay, 14.780. 14.780. We wish to round this to three significant figures, so we draw our line between the 7 and the 8. Is the 8 larger than 5? Yes, it is. Therefore, our 7 goes up to an 8. 14.8. Okay. All right, let's take it to two significant figures. 14.780 to 2. Right? Is the 7 larger than 5? Yes, it is. So our final to two significant figures should be 15, or 15 decimal point. Either is the same. Okay, let's erase that. Let's try our next one. Okay, 3256, 3,256. Okay. Let us round this to three significant figures. Is the 6 greater than 5? Yes. So we round up to 3, 2, 6. Now, there is an imaginary decimal point in this number. It comes after the 6. So what do we do to the 6? Well, we must put a placeholder 0 in, right? Because if you have $3,256 in your pocket and your bank wishes to round that up for you, yes, and they round it up to $326, are you going to be happy about that? I would not be happy if I had $3,256 and they rounded it up to 326, right? So we have to put a placeholder 0 in there. All right, let's take a look at two significant figures. Okay, we have 3, 2, 5, 6 to two significant figures. Is my 5 or larger? I do believe it is. So we round 3, 3. Again, if you have $3,256 in your bank and they are going to round it up for you and they round it up to $33, are you going to be happy? I would not be, right? So because the 5 and the 6 come before the decimal point, right, we must put placeholder zeros in. So we round 3,256 to 3,300. One more. What is the correct value when 3.1457 grams is rounded to each of the following? Well, let's look at that. To three significant figures. 3.1457, right? Let's cut it off at 3. The 5, is it 5 or larger? Yes, it is. So we would round this to 3.15 grams. All right, let's take a look at rounding this to two significant figures. 3.1457 to 2. 1, 2. Here's our line. Is the 4 5 or greater? No. So we would round this to 3.1 grams. Now, you'll notice, right, that if you had rounded our previous answer, 3.15, if you had rounded this, you would have gotten 3.2. But the actual answer was 3.1. That is because you do not want to further round something that has already been rounded. You wish to round the original number. Okay, so now, when we multiply, divide, add, subtract, or otherwise do things to our numbers, right, we need to make sure that we have the correct number of significant figures at the end. So what happens, for example, if you multiply or divide? You wish to have your answer have the same number of significant figures as the number with the fewest. For example, if you multiply 24.66 centimeters times 0.35 centimeters, your calculator will give you 8.631. The answer 8.631 has 4 significant figures, but your two original measurements, one has 4 significant figures, one has 2. Your answer should have only 2. So when you multiply 4 significant figures by 2 significant figures, you should get an answer with 2 significant figures. So since your calculator gives you too many, we are going to round. 8.631 rounded to 2 significant figures is 8.6 centimeters squared. Keep your units. Okay, multiplying and dividing. 21.5 centimeters times 0.30 centimeters divided by 1.88 centimeters. Using your calculator, you should get 3.430851063, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 significant figures. All right? Since the first number has 3, the second number has 2, and the third number has 3, your answer should have the same amount as the fewest. Well, the fewest are 2. So let us round this number to 2 significant figures. That would be 3.4. And then, of course, we are going to keep track of our units. We are left with centimeters. What do you do when your calculator gives you an answer that has too few significant numbers? For example, divide the following measured numbers. 6 grams divided by 2 grams. Using a calculator, that would give you the number 3. However, the first number, 6.0, has 2 significant figures. The second number, 2.00, has 3. Your answer should have 2 significant figures, but your calculator only gave you 1. In that case, you add a decimal point and as many zeros as you need to get to the correct number of significant figures. Remember, a trailing zero is always significant when there's a decimal point. So adding a decimal point and zeros automatically adds significant figures to your answer. Let's look at one more. 5.00 centimeters times 3.408 centimeters divided by 2.0 centimeters gives you an answer of 8.52 on your calculator. The first number has 4 significant figures, and that is a typo. That should say 4. 4 significant figures. The second has 2. Your answer should have 2. Therefore, the final answer is 8.5 centimeters. This concludes Chapter 2, Part 1. Thank you for listening.